Hey, Coffee Compiler Club. Here today to talk about compilers and whether or not we should do SIMD things. Oh, yeah, three different people talking about SIMD things this morning on the Discord. Oh, and I don't know what was the how fast can I search for strings is another variant of the billion row challenge. How fast can I find some count of needles and some count of haystacks and other such things. Everyone's been recorded. I think everyone's heard this before. And that's the end of my normal spiel here. Anyone want to? Well, here's Ian now. So actually, we should have people ask Ian about his register allocator because, why not? Hey, Ian. So like several people got inspired from your last week's talk about register allocation.
That's good. I saw some positive comments. I'm glad I wasn't just messing around doing useless stuff.
No, it was a fun go round. The register allocator was very, I want to say, very approachable. I don't know. I thought a bunch of the stuff was good. It was all good.
Yeah. Would I mean when I did the register allocator stuff, it all seemed kind of I was people told me it was obvious in paper reviews and things like that, and I was like, well, if it's so obvious, nobody why has nobody done it?
Right,
Uh,
exactly. I have been on the receiving end of that several times before. Yes, this
yeah.
is obvious. Okay. Where's the paper? Paper's a lot of work, actually, but just because it's obvious doesn't mean it hasn't been done or hasn't been done well. There's plenty of strawman variants that didn't work out, so no one said anything, but they said it was obvious.
Would I went round lots of people before I started doing it, asking them, and tell me I'm doing something stupid, or tell me what's obvious about it, or what should I be doing? And I hadn't seen the tree scan work. I think that was a legitimate criticism of the first version of the paper I wrote, and the tree scan works very cool, but it has this problem that it can't see things in the future. Um, and so it's suboptimal.
Well, everything's suboptimal. But no, your stuff looked I don't know. I hadn't seen it. It looked cool. It looked reasonable for what it was trying to accomplish. It definitely has some advantages there.
I think I could probably in like a space of like 2 weeks go and rewrite C1 for register allocator to use it, and
Oh,
that would be
C1 was such a well, when I played with it last, which was a while ago, it was such a mess. So
they messed it up.
it needs a rewrite, that's for sure.
That's the thing is I don't want to volunteer to rewrite something, and
No, I get it. I get it. Having watched that talk, though, one of the things that struck me was the observation that most wide ranges had very few neighbors, and that you could quickly filter by saying you were within or without of a block. You crossed the block boundary or you didn't. And the C2 graph coloring thing, I did a bunch of work to cut down interference graph edges, mostly having to do with pre-binding people due to register calling conventions. So if somebody's
Mhm.
bound in RSI for the call and somebody's bound in RAX for a call, then there's no interference. They can't be in the same register. That cut my register, my interference graph by like a factor of five. It was big. But
Yeah,
the thing that you showed should be orthogonal and could, do another big chop on the size of the interference graph. And then this is the size of the interference graph is the runtime on the register allocator. The
yeah.
big chunk is build that interference graph.
So yeah, the so I was generating code for Dex, and I was being paid to do it. So it's always good to get paid. Um, and there's a reason that Java uses bytecodes. The you know there's a lot of stuff that was done early on with the Dex stuff where they were talking about how much smaller the Dex files were, but that was because they were merging constant pools. Um, but they merged constant pools, but they didn't increase the constant pool index,
Right. So
which is just like horrendous.
we can
So
double.
they did all of these things with the instruction encodings, which are kind of like cute things. Like they wanted to put the register into a nibble, or it's either a byte or it's a nibble, and
Right.
things like that. So what they did for invokes, because it's bytecode to bytecode, um, is they have a version which can take 5 arguments. Now there's no good reason why it can't take 6, but they decided to make it only 5. So if you're passing 5 arguments, you can choose any of the low 16 registers because hey, we're using nibbles. Um, and right, and as soon as you need any more arguments to a method, then you have to pass it as a range, a contiguous range. And what I wanted to do was
Contiguous
to,
range of registers,
yep, but they've got 64K of registers,
but they
so
have to
you could
shuffle to get them in a contiguous range.
right, but then the shuffles cost you moves. So the original register allocator they did for this was a graph coloring register allocator. Okay. But the graph coloring register allocator just went, oh yeah, you can have this register, you can have this register, whatnot. And then they would fix things up. Okay. And the way they fixed things up was they then reserved 6 of the low registers for as like space they could move things in and out of. Um, and so they did a graph calling retro allocation, but then the kind of the I forget the term for like making so it fits to the machine constraints meant that they increased the code size by about 30%. And
Like hack
so
on hack on hack. I'm like, what the hell? Fine.
well, that's what I was going after fixing was like, if I can play games like, hey, you're doing, string builder stuff. So I can throw away the return value. I can know it's lying around in this register, and I can align all of the registers such that I'm not moving it around. I will save on code size. So in the paper where it's talking about pre-allocation, those are the games that are going on because basically when it's register allocating, it goes along assuming everything's going to be good, and then when it sees that it's done something horrible, it goes, okay, I'm going to go and fix up for that case, and then it does a pre-allocation to kind of like avoid unnecessary moves. So it was doing a lot of kind of like going back and doing things. It was
This is the C1 version, or this is the Dex? Dex on
This is
the
actually, I never did a C1 version. I just
fine.
yeah, I have a mortgage to pay. It's
Yeah, right. Okay.
yeah, no, and so there were things like for Dex, if you put long and double values, they do a long and a double is across 2 registers.
Uh,
If you put that on even numbered registers, you get more performance out of the interpreter.
sure.
Uh, yeah, so there was lots of things, but those things were relatively rare, and you would go around and do them again. Um, it's yeah, it's only when people start trying to optimize Java code by being super smart, so not using just regular string builders and just kind of like having their own string builder and doing everything themselves. So you can't play the string concatenation games and so on.
Mm.
But I even though I did it for Dex code, it's linear scan, so you can use it in a whole bunch of places. And we did an LLVM backend for art because that was well, I shouldn't go into why, um, but
I assume the Android would have lots of C code floating around at the low end. So you're going to have a C compiler. So there's LLVM. So now you got an LLVM lying around because you're using it.
what
So why not?
Yeah. I mean, we had LLVM learning. There was a thing called render script, and in early Android, what render script was used for was like the animated backgrounds on you had like an animated wallpaper,
Yes.
uh, and that was its kind of like major use case.
Uh,
And
this
then people
entire
wanted to do so.
language designed to make my wallpaper dance.
Well, the motivation was that uh, you if you took something like OpenCL or CUDA or something like that, then they were assuming that you had access to a GPU, and that wasn't a given on Android. So they wanted to have a SIMD language and so on. that you could write kernels in and so on, which wasn't making the assumption that you had GPUs. So they did render script, and then they were going to get rid of render script because hey, it's only being used for these wallpapers. But then they went, oh, we really want to be doing more computational photography. And at that point, it was like, oh, okay, we've actually got another use case for it now. And I'm assuming it's dead now. I think, Vulkan and other things have come along. Halide would be the obvious one. Um, but yeah, LLVM was lying around. People were saying things about Android and saying it needed to be architecture agnostic because why don't you love our architecture and things like that. And so a strategy for that is to say, oh, we'll just do an LLVM thing. But the LLVM thing, LLVM is trying to do whole program optimization. So you have like every instruction has like it's SSA, so it's a definition, but it also has all of its uses, and those aren't just uses kind of like within the function; they're within the whole compilation unit, and so they use skip lists and things like that to make this efficient. But it's a huge load of overhead if what you're trying to do is just like JIT some Java code.
No,
Um,
no, no. Uh, Arthur here.
and
Tell you about
the,
jitting with LLVM. Yeah.
there's the B3 the B3 stuff that WebKit did kind of found the same thing, that LLVM was too heavyweight for this kind of stuff. Um, with when we were doing it, the register allocation was like 50% of exit of the compilation time.
And what
So
was the compilation speed relative to C2?
uh, right. So but
You didn't have to really
you have to get
compare.
C2 onto Android,
Yeah, right.
and no people, yeah, the chances are it wasn't going to look very favorable. So why spend a lot of energy to get numbers which weren't going to make you look good? So
Which you're not going to use anyhow. Fine.
yeah, yeah.
All right. Yeah, makes
What
sense.
they do, so like the Chromebooks now, they let you kind of like run an embedded version of Linux, and so IntelliJ is kind of like the Android Developer Studio story, and IntelliJ is written in Java and runs on OpenJDK. So they do things like run a container with OpenJDK inside of it, so that you can do Android development inside of Chrome OS.
Okay.
Yeah, yeah,
Yeah,
yeah.
exactly. I think actually I did some Android development on Android for desktop or something. And I remember there was some extra layers thrown in there that just made it miserable. And I switched over to Node, which has its own miseries, but there you go.
I used to go along to like Google Summer of Code things where people were making video games for Android, and sorry, making open source video games, and I was always kind of like curious to see why they weren't doing it for Android, and it was always just like the developer experience was miserable. And
Which just shocks me or surprises that Google didn't figure out the developer experience on Android. That I mean, that should have been their reason to enter,
but
whatever.
well, they were trying to push it, like the build system for like for Android projects by default is using Gradle, and Gradle's written
There's
in
your
the Groovy
problem.
scripting language. And it's like, why? Like, how many game developers want to write Gradle and Groovy? It's like zero. It's
Zero. Yes.
yeah. Oh,
Fine. All right. What else? Oh, Levo and how to build for yes without Gradle. Oh, C for Android. Levo's asking how to build C for Android without Gradle.
I've done a little bit of that stuff. So Android by default has this native activity, and you can use that to then like not really have to write any C code because it like load a shared library, and then you have a bunch of like glue code that does all the like Java C interaction stuff for you.
I want a different
Uh,
thing. I want to write C code on Android without Gradle. I want to write C code, but
yeah.
not have Gradle involved.
So once you get the native activity, you can then just use a shared object and do it all in C basically. And then there's like some glue code that
Ah,
people have already written for you, and so you can then interface with some of the. I think there are pieces of Android that are like userland facing stuff that are Java sided, and so you still do technically need to talk to the Java side, if I remember correctly. And
Yeah.
but people have done that sort of stuff for you. I think there's a demo somewhere online. Let me pull it up.
if you
So,
find one,
so
throw it in the
you,
links.
so the native activity is basically a Java application, but all that Java application does is a JNI call out to your C main routine, and it takes over. But all of the interesting things you want to do on your mobile phone, you want to do. You want to be able to make phone calls. You want to be able to get GPS locations, all of that kind of stuff. And the way to do that is with intent, and all of that stuff is done in Java. So then you need to be doing JNI calls, and so people can wrap it up.
Wow. Okay.
This is a very old example, but it did it with this one did make, and it just built a shared object with Android glue stuff.
Hmm.
Sorry, I'm playing secretary and playing catch up, and I wasn't doing a good job. So I'm
Yeah,
trying to remember what we just talked about here.
that it was kind of it's kind of a shame that there was a story in Android. So I first went to like to visit like the Bay Area in 2000. I think Cliff was out of town, so I went and visited the Azure guys. I went and saw people at Stanford, and I saw like Dan Bornstein, who's like the Dalvik lead, and they would at that time in Froyo Android, you couldn't have any C code. Everything had to be Java, and adding like the ability for users to write their own native code was going to be like the answer to the performance problem that they had on Android. And so they weren't doing a good job of improving the Java performance. Um, and that I think that's why like so many people were glad when Arts came along.
Hmm.
But the NDK has issues in that you've got a bunch of engineers and they've got an opportunity to optimize things, and so um, there were premature optimizations. So they made the pthread mutex on ARM32 a single integer, which is like kind of like, oh, look how smart we are. But of course, you embed that data type into your program. And if somebody wants to kind of like have a Sparta pthread mutex, you can have a pthread mutex, which is an integer, but if you don't know if you've got contenders or not, and if you don't know if you've got a contender on the lock, then the only safe thing to do is to always assume you have a contender and try and wake them up. But that, of course, that means doing a system call.
Yeah.
So
Yeah.
So they had a pthread mutex which was doing unnecessary system calls, but you couldn't change it because you needed a little bit more space,
Right.
and the size of an integer was baked in from the first release. Um,
Ouch. Yeah. Right. The
but
Java folks did some count of bits on an object to say that you were locked, and then as soon as you were locked, you just put a side structure, and the overhead was always getting from the Java object to the side structure, and the side structure had shit like contenders or not, and counts of how
Dave,
much we could spin weight or whatever.
David Bacon gets a lot of credit for that, and so the state bits often get called Bacon bits, which is
Yes.
just awesome.
Yes. Well, that was the running joke for many years, but bacon bits. And honestly, it worked out really well. I think Azul did a little better on that front after a while, but there was something akin to bacon bits, so we all considered them bacon bits.
Wait, I did a paper. The first paper in this area, I was talking to. Do you know Mike Burrows? Um, so Mike Burrows is kind of a very old Google employee, but he's been around. He was in the Java space, I think with
Yeah, I've met him
Synapse,
before.
Signosis, maybe I forget. Synapse probably. But he had a paper that he deliberately made very obscure about quickly reacquirable locks, and that's where all of like the bias locking type ideas come from. Um, and if you explain to him something that you did in that area, I did the paper on learning locks, where the problem with bias locks is the cost of revocation, and so you can add some amount of learning to make it so that um, you if you have something where you know that you're never getting revocation, then let's use biasing all the time. If you get some revocation, then let's try and make it so that you don't do that. So you have to have some extra state hanging around to dork all of that. And so I did this learning logs paper. Pislow did something similar.
Because at Azul, I redid the bias locking. We had much cheaper stop an individual thread. So if somebody wanted the lock and the owner was running it biased, the cost to have him check himself and unlock it if he wasn't supposed to hold it was actually pretty low.
Right. They they they've gone the OpenJDK has gone in that direction as well now. So the the seg faulting to run everybody into a single global save point stuff. But what they were doing as a first hack to get that in was they had like a return barrier. So what they would do is they would make it so that return barrier would immediately fail, and then you could get a thread to suspend, and it didn't look like you were getting rid of the giant global, M protect on a page type running people into a save point.
Uh,
Um, so the GC people get really excited because they're going like, return barriers have got a use case, and it's like, yeah, but mainly for save point suspension.
no, just do the one thread at a time save point thing. Just so cheap. Like, fine. Yes, that was my first big hack. People here occasionally talk about big hacks. My first big hack at Azul was redo the entire runtime system for starting and stopping threads, for throwing exceptions, and getting the C1, C2 runtime to all coexist. It was all tied up in a knot. And that took me 3 months. And at the end of that, I had 5,000 lines of new code, 10,000 lines of changed code, and 10,000 lines deleted. So it was a net negative of 5,000 lines with a lot
And
of changes in
I
there.
was there.
Were you there for that one, for that putback?
Yeah, yeah, that's where that's I joined just on the start of the x86 transition, but I
Ah,
still had to do some Vega support.
well, I did that before. That was the first thing I did at Azul, I want to say. I rewrote that so we could get a C1, C2 thing. No, it wasn't the first thing.
Yeah,
You're
yeah.
right. We was
It was
at the
I
new
was
building, maybe. All right, fine. Oh,
no,
gee.
it was still in Mountain View, and Marty was there working with us on it.
Yeah, yeah,
Yep. So
that was fun.
all good
All
stuff.
right.
I'm gonna have to drop in 5 minutes. I'm afraid. I've got another
Okay, we should
meeting.
we should switch topics anyhow. We're reminiscing about working together at a startup that's still around. Fine. Okay, let's do something else here. See, I tried to talk Adrian into showing off his stuff. He said no. Does anyone else want to throw something out there?
I
I can
guess
throw something out.
go ahead.
Just show you how I've spent my week working.
Oh, that was a
I've
weird
moved into
backdrop too.
VR.
Oh, geez, that's
So I've spent the last week working inside my new Vision Pro toy all the time.
the
It's
the
surprisingly good.
the view we get of you now on Zoom here. This is very uncanny valley.
Yes. Oh yeah. It actually looks worse than because I constantly trying to look at myself over here. I have to focus on you, and then at least my
No,
eyeballs
no,
aren't
your
going
face
off
is
to the
messed
side.
up. It's like it's faking your lip movements badly.
Oh, that's true. Yeah, I've avoided so I've been doing Zoom through here all week too, but I do not turn my camera on for fear of freaking out all my coworkers.
So why, but why is this way? This is just like a standard webcam on your monitor? It's
No, no,
not.
no, no.
No.
No, this is I'm inside a VR headset, right? I'm not sitting at my computer now, and the VR headset has cameras that are recording my eyes and my mouth and then mapping it into my
Your
virtual
avatar
persona.
thing. Yeah, okay.
But
This is
yeah, but in I'm working inside VR, so I have like multiple like huge like, 100-inch monitors surrounding me. It's I don't know. It's an
how's it
experience.
working then? That sounds very weird.
It's almost as good as the real world. So that's the thing is normally I work with two 5K monitors and that's still a little bit better than this. So
Uh-huh.
But if I want to look like a dork when I go to the coffee shop, I can have tons of screen space away from my desk.
I see. Mostly though, the view I'm getting on you is very freaky. For
Yeah,
yeah.
yeah. This is not the best part.
Okay. I'm
So,
all prepared for new AI overlords here.
yep. Oh yeah, it's the new world. So,
Jeez.
We call this view the Mark Zuckerberg.
oh my, yeah. The first time I recorded myself for this, I looked so much like Zuck that I had to delete that one and try again to look a little bit more natural.
Go for Beyonce.
Go for what?
Beyonce. Beyonce. Pop star. Taylor
Oh,
Swift.
no, you can only be yourself. I just happen to look a lot like Zuck when I recorded myself the first time. I don't think I have a Beyonce look to try. But anyway, I'll turn the video off now so as to not disturb.
That is disturbing. Wow. There you go. Your kid's diagram from years ago. That's
Yes, yeah.
much
Yeah.
nicer.
That's
Much
that's a
more
better version of
lifelike.
myself. That's what I looked like 10 years ago.
Excellent. Excellent. I don't want to look at myself from 10 years ago, my driver's license from 10 years ago. The hair is getting whiter and thinner. It's not improving. Fine. All right. I don't know. So Derek, you were going to volunteer something.
Yeah, so I've been playing with, I had this idea of using lattice types from the compiler, making them sort of useful to the user. So basically being able to say type of X and it just gives you a lattice type. Uh, and then you can do things like you can basically do is type stuff right in the code.
Right.
And so far, it seems I just threw it together last night, but it seems to work fine.
I've wanted to do this for a long time. That seems clear. But user supplying the names, but they're forced into writing a lattice, and then they can use the types as a arbitrary type
Yeah,
scheme.
yeah. So, I basically have three node types in the graph. There's a like a type of node, which
Uh-huh.
will give you your lattice type, and then uh, um,
Is a
there's isa, and then there's a type node. So basically, the type of um, well, like the type node is something that I use for like uh, the built-in types. So like the sort of
int
bottom types.
float.
Yeah, I put
Yeah.
put all the bottom types in,
Yeah.
and that way I can do
Now
do
you need
those.
a dispatch off of the type.
What's that?
A dispatch, a call based off the
Yeah,
type.
yeah. So right now I'm thinking that there's no real run. This stuff doesn't really exist after the compiler is done. So
Well, if you say type of, you got some constant data in the register. So something exists after the compiler's done.
oh yeah, I guess I could actually just create a constant. So far, I was just thinking that I would say, well, if you resolve the type, then great,
Mm.
and it'll work. And if not, it'll just give you a compile error.
Compiler error and say, yeah, yeah, okay.
So yeah, but yeah, I guess you could just throw a constant into a register. So yeah, we'll see. But
Interesting.
it's
Interesting.
kind of handy because sometimes I want to send like I need to shuffle data around on the PE and I need to know if it's a 8-bit or 16-bit value and before I was having to write like specialized versions of functions for each variant and call the right one. But now I can just put a type check in and carry on. It's much, much nicer. So
Sure.
yeah.
Sure. I mean, yeah, exactly.
Yeah.
I was always wanting, so I do a lot of compiler obvious work and I do a lot of compiler transforms. And a lot of these transforms have properties that are sort of easily checkable.
Yeah.
And then they could say things that's okay to commute, to associate, to distribute, to invert this or that or whatever, or it's not because you missed some legality thing and there's no support in the language Java or C or any language ever used to do these things at a higher level. So you
Yeah.
hand code all your support, like the peoples have all these rules but all the rules I do to support them are all manual boilerplate kinds of things. And
Yeah.
I've wanted, I've thought about this when I was starting at A to bring out a user exposed typing system where the user could say, okay, I have the following properties and I'm going to force you to write them in some kind of a lattice, but then you can put them on elements and do meets and joins and have the compiler track your types with meets and joins and tell you things like, oh, you're associative, so I'm going to reassociate this expression. And that's okay or not, or whatever it's going to be.
Yeah. Yeah. So, I mean, so far, it does what I need,
There you
and
go.
it's pretty easy to get it set up. So I'm pretty happy with that.
So when you
It's
say
definitely going
you
to
have,
make the end result language that people can use a lot more powerful and cleaner.
oh yeah, totally. Yeah, and honestly, if you're just doing type of on ints and floats and whatever, you're basically secretly jamming in a size of the operator. You have another way of an enum for the size. So it's not
Yeah,
like it's big, deep theory here at all. But it
exactly.
definitely sounds useful.
Yeah, and actually, like that size thing was the first function I wrote because I need to sometimes send data over a socket, and you have to send it byte by byte. And so I thought, okay, just you can give it now. You can just give it data, and it'll say, oh, okay, you're looking at bytes, so it'll send 1 byte per item or 2 bytes per item.
Right, right, right.
So
You doing socket communications off chip
within the chip.
within the chip. Interesting.
Yeah,
Okay.
yeah.
Uh,
So, and the other thing I got going the other day is a nice little sea of nodes evaluator. So very much inspired by the one in Simple, but with like with the ability to do the um, like PE operations as well. So
man, right,
yeah, so I
right.
feel like I'm making good progress. I don't know. It's been good progress for the last couple of months. It's like,
So at some point you put a fuzzer in,
yeah, I haven't built
breaks
the
you.
fuzzer. That was on my to-do list, and then I decided I was like, you know what, I'm trying to get this project done as soon as possible, and so I was like, maybe I'll delay the fuzzer, and I can't decide whether delaying the fuzzer will make the
Right,
projects take longer or shorter time.
right. I don't know. I don't have any users of Simple other than, myself and the fuzzer found stupid things, but I found plenty of them that were also relatively easy to fix. One or two things made us rethink assumptions. Mostly they were easy to fix, and it just bulletproofed the thing a little bit. And that
Yeah,
meant should a user show up, they won't fall over the stupid things that were happening.
yeah. I'm definitely glad I spent a bunch of time bulletproofing at least to some extent, a few weeks ago, because now as I've been adding features, they
Mm,
basically just work.
they just come
And
in. Yeah, that's always nice.
yeah,
We did that for Simple on the types as well, and that fixed a bunch of stupid issues. Um, the types are easy to bulletproof, but
yeah,
and they pay off. You
yeah.
can also bulletproof your transfer functions with a little more work, and that's probably going to come up on Simple at some point too. They have
What
to
do
be
you mean by
monotonic
that?
or you fail, and the monotonicity check's not too hard to throw a
Yeah,
test driver for.
yeah,
I probably complicated my life a lot by doing this, but in my lattice for integers, I also have known bits. So I store like a set of bits for the
Yeah,
known ones, known zeros, and then from there I can like know whether or not like, oh, if I do any masking operations or casts and stuff, I can know, oh, these top bits are zero, and therefore I can get rid of this cast. Um, but it complicates writing the like transfer functions now because now I have to like propagate that kind of information. Because if I do a replacement, like let's say addition like x plus x, that needs to track known bits in the same way that shifting up by one would. Because if I were to do a transform between those two, there's like a potential case of either do the shift or do the addition, and both of them should result in the same answer because they're
yep.
themselves interchangeable. And I do optimize from which direction do I go? I think I do x plus x to the shift. And so like if it doesn't do that correctly, then it'll yell at me with the forward progress asserts.
You can you can always throw away info if you don't want to deal. And then your known bits get confused and lost when you pass through whatever X form you do.
Yeah.
So that's a back out. I don't care now. I don't want to deal. Like, hey, known bits on a division operator. Well, yeah, maybe not.
Yeah.
Yeah.
But yeah,
So
the
one of the
thing
things,
where you switch an add and a shift and they go back and forth, I call that something closer to like the one-step church roster. You go around two sides of the diamond of transforms. I transform the add or the shift and the add, and I went in the same spot. And that's
Yeah.
not going to that's not monotonic as a separate thing. That's a different property you have to go after.
yeah,
And I've been doing that in the AA, but I do it a different way.
yeah, I don't know if it's relevant to what you're talking about, but and I'm not sure if this is what you do, Cliff, as well, because I don't remember. This is some old code that I did a long time ago. When I'm meeting binary, or when I'm doing doing a meet where there's a binary operation, uh, sorry, when I'm calculating the type of a binary operator, um, I do what this thing I call a cross join, but I basically run the operation on the min max and max min and all the combinations. And then I can just figure out the minimum and maximum that I get from that, from doing all of the combinations of binary ops. And then that's the new type that I do. So I can try and keep the range type as precise as possible.
Oh, I see. Yeah, no, C2 did ranges and not known bits.
Yeah. So I'm
And
doing
and I
ranges.
did the range math for all the common operators. And then there were places where I just, blew it off. I didn't care. It was too much.
Yeah. So yeah, I do that for comparisons. So like
Okay,
comparisons are a bit tricky with ranges, so I just don't bother.
don't bother. Yeah, fine.
I just look for
Um,
like completely like the full ranges don't overlap, or they do overlap, or they intersect. I look for that
right.
stuff, but otherwise I just
Just give it
say
up
I
after
don't know.
that. Yeah. So I did the ranges for the masking thing that Yasser you were talking about, but only on 8, 16, 32 boundaries. And that was because people in Java would be loading things and then masking all the time. And as soon as you knew you had a range, you could tell that I could store or load or keep it as a byte or whatever. There was a bunch of things. Because the biggest one was when longs and you didn't have 64-bit registers, you had 32-bit registers and you're doing long math and somebody wants the low bits or the high bits or whatever shifted by 32. You could do a 32-bit load of the correct offset or a 32-bit store and skip the mask.
For C, the main case that comes up for C is that the integer promotion rules make a bunch of like smaller types into 32-bit integers, and
Right.
so there's a bunch of random casts and truncates everywhere. And if I don't like track enough bits, I don't end up eliding some of those casts, which is
Right.
annoying.
Java's rules are basically everything that's sub-int gets promoted to int upon loading from memory, and now it's just an int until you store it, and then you have to cast it back down.
Hmm.
Just a little different. I remember doing C compilers and tracking known bits long time ago, but never very far. Never not in the type systems, so never very far.
Yeah.
Short people ops. When did I do the C compiler? I did one in undergrad. Oh, early grad school years, I did basically C compiler to a backend, and it was doing the same kind of things. Free C of nodes. Okay. All right. Looking for another topic. This week I've been hacking on ecstasy code, but it's all about tree rewriting for Elvis operators. It's very boring. That and my wife skipped last week. Did I tell people this already? She found some paper that said something about you can't skip past a certain age. People of a certain age can't skip anymore. And I was like, bullshit, I can skip. So I went skipping around the living room. And the cat thought this was fun. The cat followed me afterwards, having fun. Lisa, this looks great fun. She went skipping around the living room. And we circled the cat tree tower, and then she twisted her knee. And she can't skip now. And week on
So the myth
crutches.
the myth is true then?
Yes, the myth is true. And week on crutches, and another week half crutches, and I've been driving her everywhere. So all the things that she would normally do, and she goes to work and now she's going to work and not going to the grocery store and not getting this and not getting that. So I'm doing all those.
This was like a sprain, not like a tear or
No,
something.
this was a meniscus tear. She
Oh
has
no.
mild osteoporosis in the knee, degenerative for age, knee
Yeah.
tissue, and then the meniscus is wearing and it tore. And there's no saving it. And some point down the road, she's probably going to get a pair of new bionic knees, big
Wow.
old $6 million man. She's going to have mechanical knees, whatever. Set off all those airport scanners, things like that.
So she, in the meantime, is she doing physio type stuff? Guess so.
Yeah, well, it's mostly stay off of it while things
Initially.
heal up as much as they'll ever do.
Yeah.
So we have crutches. They're used occasionally now. Last week they were used a lot. Now they're used occasionally.
Mm.
We're trying longer walks. I mean, she's a supervisor at Starbucks. She would normally be on her feet for a 4 to 8 hour shift, and that's right out. Um, so can you walk to the mailbox? Well, it's a quarter mile and some hills. Turns out, not quite yet. Walk to the mailbox. But I don't know what other things we did last week that we were stretching just to see, and it's getting better, but it's not there yet. Fine.
Yeah. I like to go out and play soccer or kick a soccer ball around and stuff, and it's a high knee risk
Yeah.
thing.
Right.
So
Right.
I I actually do a lot of sort of preventative knee exercise to try and strengthen
Oh,
them.
there you go. I'd say that's a good job. Good thing for a 20-year-old, the soccer and the knees, and
Yeah.
maybe okay at 30, and somewhere between 30 and 50, you gotta kind of like squint at it.
Yeah, exactly. So I'm my theory is that strength is important, so
Yeah,
just
right,
do the strengthening thing.
right. Fortunately, I live out in the country in the mountains, and there's lots of opportunity to do outdoor yard work. So I get my yard work for my exercise now.
That's good.
All right, what else?
Yeah, that's why you could do the skipping.
Yeah, there you go. There's no end of steps or standing on a 30-degree slope while trying to weed whack or whatever. There's things that will get your balance back and get your strength back and all kinds of stuff. Yeah. Yep. And good hikes and big trees. So that's nice too. Although we're waiting for the rains to quit, they kind of sort of are thinking about quitting, and everything is green and growing incredibly fast. Welcome to California here. All right, what else I was going to say? Ecstasy doing Elvis things. That's a lot of tree rewriting and nitpicky, and no terrible deep theory, but just has to be done.
I guess in some updates I wrote an implementation of the paper that Ian wrote about register allocation.
Oh, wow, you're not the only one, but yeah, go.
Yeah, I've mostly gotten the allocation aspect of it. What I'm planning on doing next is I need to build a sort of framework around like splitting because it's not like it doesn't seem like it's particularly like register allocator specific, the actual act of rewriting the graph.
Yes.
So I can generalize that and then throw that somewhere else and then have all the register allocators all share that and then they all say like this is the thing I want to split. I want to split around things
Yeah.
and stuff like that, but like the act of splitting can all be sort of generalized. And so that's what I'm working on next because right now it's very low quality because it spills.
Okay, right.
Yeah,
But not splitting. You're doing splitting.
or I'm working on that.
You're working on
But right now
splitting.
it's only spilling, and
Oh, okay.
so
Yeah.
the Ian paper it effectively is it's basically just linear scan at its core, except instead of storing all the live ranges, you just don't spend the memory to do that, and you
Yeah.
just do
No,
the
it's a
queries on the fly.
really nice
Yeah.
technique there. So I tell you what I did in C2 is I gave up trying to incrementally rebuild the interference graph. If you split, I just rebuilt everything. So you got phases where you would build it. It's expensive. So you color as best you can. You got some fails. You split them all at once. You threw away the interference graph and you rebuilt. Now, is that good or
Mhm.
bad? I don't know. For super fast, there's faster. That's a linear scan. or slower if you're doing LLVM or replacement for LLVM. Maybe you don't care to rebuild. You just rebuild, skip all the bugs from being incremental.
Ironically enough, LLVM just has gotten away for like the last 20-ish years without like doing graph coloring. And it like bites them sometimes, but like they just kind of like held up with that, which is kind of surprising.
Yeah. Yeah.
Like the big place where I remember hearing about it biting them was to do with when they talk about like inlining. It's like, oh, you can't inline too much or else you might have too many live ranges and that starts to bite you.
Yes.
And so it's things like that where like I start noticing the performance knee you talked about before.
Yeah. Okay. There you go. That's nice.
Yeah.
It's kind of surprising to me that they wouldn't. I mean, LLVM doesn't seem like it's limited by compilation speed. And,
right, exactly. Why not even give it a go?
They've got like a optimized for speed register allocator.
They're very easy to think about and start with too. So I'm thinking somebody started with one and then they get wound up around many other things. And the knee in the curve for performance of too much inlining, to get the gains out that you want, you also now fiddle with inlining rules. And then your LLVM, so you're targeting 15 different chips. And so you have to go deal with that. But Hotspot dealt with 15 different chips. So I don't know. There's a way to do a register allocator here with graph coloring and then turn.
So I remember Latner, I believe Latner had some opinions about graph coloring to do with the important thing being more to do with better spilling and stuff like that. And that was one of the reasons why they stuck with that decision. So like originally LLVM was linear scan, and then it became greedy at some point. I think like 10 years ago, and then greedy was like it's basically just linear scan except like out of order. So it like it just prioritizes live ranges based off of like some heuristic. Like, oh, this thing is just, you know, this, I would rather this thing get a register, so let me like allocate it first.
Right. Yes, this is a hot loop version thing.
Yeah.
Yeah.
And then it splits like around those earlier decisions. And then I think it has some like recoloring stuff. So I can sometimes like try to see like, oh, you know, I've split. So let's see if we can try to fix things up. But it doesn't like retry the graphs in the same way that like graph coloring algorithms generally do. And it also is just not graph coloring. So it doesn't, well, it doesn't get the same colorability stuff.
The thing with the graph coloring is that once you failed, and you always fail,
yeah,
you now get in the split, and then splitting is a key performance hack here. I think you get a lot more flexibility, you get better allocations in general, but you can blow it all if you spill badly. And splitting, especially splitting around hot areas and or around high pressure areas, work out. I mean, they'll let you get that good allocation, but you have to pay attention to where you split, where you spill.
Yeah.
Is there a priority version of of graph coloring?
Always.
It's always priority.
Yeah, when you say priority, so what it really does is he throws out from the, once you build the interference graph, you now throw out everybody who gets trivially gets colored, because you don't care because they're going to get colored. This reduces the interference graph to get these cliques that are too big, that you can't guarantee a color. Now you throw people out that you hope will get a color, but you can't not guarantee. And so you empty, and then you unwind in reverse, put people back in, and when you come to this clique, and the guy who threw out, you couldn't get a color, you couldn't guarantee a color, he maybe doesn't.
So is that throwing out and the putting back in something that's basically priority order?
No, it's not frequency based or program based. It's just simply looking at the number of neighbors of a live range. So if you have a 16 register machine and you got a live range that's got 15 neighbors, you guaranteed you're going to get a color. So don't worry about it. He's going to get a color. He's going to get a register. So throw him out and keep going. That brings the graph down to these cliques where you cannot guarantee. Okay, once you failed a color, you got a set of guys who didn't color. They have interferences with the cliques around them, and they have space in the graph where it's high frequency and low frequency and high pressure and low pressure. Now it's a spilling game. And the spilling game has nothing to do with graph coloring versus linear scan. It has to do with, I couldn't get a color no matter how hard I tried here. Now I want to break up this big live range. And so now the priority is that when you say priority, I'm thinking this is the priority you mean, it's frequency. So I have this hot use in a loop. I'm going to split around the loop. So I'll get a register for the loop, I hope. And if it spills on either side of the loop, I'll get a loader store before or after loop bounds, fine, whatever. Same kind of deal where I stretch it over a long space, and in between there's some high pressure areas. It's probably going to not color again because there's too many registers in those high pressure areas. I'm going to spill it around those. So it's how you spill is kind of an independent thing. And once you've broken the graph up, now you go back to color again. And here, graph coloring says, I'll color this thing where a linear scan says I can't figure it out and I'm going to have to spill again. So you get the better spills or the fewer spills because of global knowledge lets you recognize it. I don't need to worry about this guy right now. I'm going to worry about him later. He'll color. So get him out of the face and color everybody else. And oh, look, they all colored. When I come back around to this guy, he's guaranteed going to get a color. So I'll do him now. Whereas a linear scan guy has to say, right here, right now, give this guy a color. But I don't know what's coming up. So I can't tell what color to give him.
Okay.
But yeah, there's the graph coloring is pull everyone out and then put everyone back kind of a thing based on interference. And the thing that Ian said was basically a whole lot of guys who don't span a basic block boundary are going to color independently, and you can split the problem into people who cross basic block boundaries and people who don't. And the interference graph hack is like, that's good where you cross the basic block boundary because the interference, the interference edge of the live range. So I'm trying to say live range comes all over the map, has holes and stuff, and that kind of naturally flows out of that. And as soon as you're local within a block, you don't need to be in the interference graph with a tiny count of neighbors only to get thrown out again. And that was the thing that C2 is always doing. I mean, I tried hard to shrink the interference graph, but still, you had a live range, it went in the graph, it had no neighbors, so it came out of the graph. Well, I just like skipped putting it in and taking it out because the graph was this n squared thing. You triangulate it and cut it in half, blah, 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 but it was order n squared. And that was your n squared running time on C2. You cut the constant down as best you could, but a better way to do that would say 80, 90% of the guys don't need to be in the graph. I'm not even going to make a slot for them in the graph, and I take my n squared and chop it by 5. Chop n by 5 on the n squared piece. That's a nice tidy improvement.
So when you're rebuilding the graph, you did actually rebuild the entire graph, including all the stuff that would immediately get thrown out.
The act of rebuilding was necessary to know what colors were available. And the rebuild was relatively cheap. So you burned a bunch of memory to build the graph. And that graph was done when you're doing this phase of it, you build it as an adjacency matrix. So on one dimension, it's indexed by a live range number. On this dimension, it's a list of neighbors you collide with. And if you keep them all as 16 bits because you only have 65,000 live ranges, which C2 did forever and a day, it's not too bad. Then the throw out meant I pick this live range. And I want to throw out him and all his neighbors. So I walk his neighbors and I go to all the other neighbors and I find him in their list and I shrink that list by 1. And I take the easy hack here is now take the guy that you pull out of this list here and put him at the end. So you just swap 2 elements and shrink the count.
Yeah.
Okay.
I'm just thinking that, and I don't have a very good mental picture of exactly how this works. I've heard you describe it 3 or 4 times now, and I still have a hard time some of the steps. But
yeah, I don't have an Eon prepped version of slides. I can write maybe something in the Google Docs.
But the question, and maybe it's a naive question, is just, can you do that initial building and then do the sort of trivial throwaway stuff and then take a snapshot, and then every rebuild can sort of resume from that point because that's the part that is sort of invariant anyway?
No, it's not invariant after you split.
But isn't the trivial stuff invariant?
Okay, well, on the rebuild side, you rebuild with the hack I was describing to you lets you rebuild in place. So when I throw somebody out, I kept the same amount of storage. I just moved them to the end and shortened the list. When I put him back in, they're at the end of the list. I just bumped the list counter length by 1. Now he's back in the list. So the throw out and the bring back in or don't take up any more space. And they're actually very memory efficient. So you can live in certainly in L2 for that operation. When you bring somebody back in, you need a color and you go visit all his current neighbors and intersect their colors. Those are the colors that are, intersect out all the colors that are in use. The leftover colors are what you get to color yourself to. And you pick a color out of that. Now that you've picked a color, you go back in the graph. And so the next guy who's coloring will visit you as a neighbor and he'll discover you've picked this color, so he has to pick that color. So you need to have them when they go back in around to get the colors, get the color choices. That's sort of the big piece of the cost is building it in the first place because it touches this n squared chunk of memory. The thing that I did with I know your register choices are limited and they'll never intersect, was to say you guys don't get an edge, which meant I still had all the Y ranges here, but I didn't go quadratic out here. I went out 1/5 as much this way. And so of the 2 dimensions, there's a triangulation, but then I got this 1/5 as well by register for calling conventions, sort of statistically speaking. What Ian was pointing out was there's another filter here, and that filter could say, I know for a fact I'm never going to get more than X neighbors and during the building process. And as soon as I know that, I've added a new guy down here and I'm counting his neighbors and he's ran out, he's done, he's within 1 block only, there's no more neighbors. I'll just reclaim that space. You never go in the interference graph. I want your live range number back. I'm going to toss you out altogether and I'm going to reuse this same slot down here and I'll add a slot when I discover you cross a boundary and I need a new, but up till then, yeah, no. Just keep throwing out guys that are trivial.
So is that an optimization then? Is his sort of filtering trick something that you could also do in a graph coloring?
Yeah, that's what I'm saying. I think they would play well together. I think my hack for cutting down the live ranges and his hack are orthogonal and they would both work. And the combination of the two could in fact be sort of dramatically better than either one alone. Like I got a factor of 5 on average at what C2 compile. Or he's getting an 80%. He's getting a 5x reduction as well. Those two might be a 25x, or they could be even stronger because they might cooperatively throw out even more things than just the divide by 5. But as soon as you get these big divisions like that, big integer divisions, you're back to being essentially linear time. You're going to be closer and closer to just being straight up linear. And I don't care no more. So I'm curious now to see if that would work out. It would give you best of both worlds, if you will. Something closer to linear scan for speed and something closer to graph coloring for quality. And then you turn all the other knobs up, all the inlining knobs and whatever else up to get all the performance out of the graph color. So, too much fun stuff to do.
Yeah, unfortunately, so many things on my plate before I can get to all the fun register allocation stuff.
Yes, yes. And when you get closer, you're going to still need to get a corpus that you can do large scale counts of, because it's all a statistics game.
Yeah. The huge thing is this is the reason why I wrote a C compiler, because I get to eat up a bunch of C code bases now.
Okay, yeah, right. You get a giant corpus. Yeah, yeah.
Yeah.
And you're comparing against LLVM, so you have a reasonable target to go say, hey, I'm better or worse. Why am I better or worse?
Exactly. I have to sit down at some point. Basically, before I'd done my massive refactor some months ago, and basically I started with the idea of oh, I want to simplify adding new targets, and then eventually I did that and started generalizing how I did register allocation constraints. And then from there I moved on to eventually I did machine nodes. And that's where I'm at now. And I'm almost done with that stuff such that I have all the operations that I used to have. I think I'm missing a few things like thread locals. But once I'm done with that and then I get bugs fixed with that, then I can go back to I think if I can get back to compiling some of the old demos, which were like image loading stuff, so like load a PNG, open up a window, and like draw on the window with it, stuff like that. I should be back to what I was at before, and it was also like a NES emulator that I ran, and a few other like cool little projects. But yeah, once I'm back to that, then I can start focusing on like fixing more bugs and hopefully getting around to fun optimizer stuff.
Who's paying your bills now?
Nobody. Well, it's like a mixture. I like live with people,
Okay.
but also yeah, I unfortunately have work, which is
Well, that's what I was
gonna
asking.
eat up my time.
So somebody's paying a bill.
Yeah,
Okay. And they're having you do
I like
real
split
work.
bills with people, but I also like I am working right now, unfortunately. Yeah, so that's gonna eat up that
I am
also eats
too.
up tons of my time, and so we'll
There you
see
go.
we'll see how many months it is before I merge back into main and I like finally get around to all the optimizer stuff.
Still bill.
Yeah, is it?
Yeah. Right up
Yeah,
until the giant OS in the sky comes and collects you,
exactly.
kills your process and throws you out.
Yeah, I've got like a half finished like inliner where it's like it can do inlining as in like it can copy graphs, but it has no heuristic powering it. So
Ah,
it doesn't like really do anything.
well, he
Yeah, I
doesn't
think it'll
necessarily
only
call.
like inline if the graph has like less than 15 nodes or something like that, which is like a terrible heuristic, but yeah.
There's a first cut heuristic, and that's a good start. It's tiny.
Yeah.
Okay.
It'll find getters basically.
Yeah, right. Yeah. And you
Or it
can
could
trace it up a little bit, and then you can start counting things like, I'm going to ignore all the fees and regions and whatever. If I
yeah.
see one test and a few other nodes, then maybe it's worth it. Get that test might inline and constant fold away.
Yeah,
Or
that's one of the spaces I kind of want to play around with a lot actually, which is to do with like partial inlining, where I like inline only the test and then I have like a fake
yeah,
like a secondary version of the function without the test,
yeah.
and then see how often that comes up because I imagine it's actually going to come up a lot, and I want to like do stats on that to see
People write code where they have an early cutout that
yeah,
is a popular cutout to take, and you
yeah,
want just
exactly.
the cutout and not the body. Yeah. C2 got that by doing the frequency based thing with the whole inline. He'd
Hmm.
inline and then he'd stop and say, this test really goes hard, this or that, and then I'll just stop and deopt right here and not carry on generating code for it. But he had to inline it first and then decide he was going to cut you off.
Makes sense.
Why not just do what I did and just inline everything as long as it's not recursive?
There you go.
I mean,
Believe
you can
me, there are
inline if
people
it's
who asked me to
recursive
do
too.
that, and those
It's like
flags
unrolling.
got turned
Well,
on, and the end result was, it was just miserable for giant, giant compiles and allocations, and everything else was just giant. It
yeah,
didn't actually was not performant.
no, but it really exercises your inliner.
Oh, it exercises meaning a register allocator. It
Yeah,
would exercise the register allocator, really.
yeah, but only if your inliner actually works.
Well, okay. So once the inlining graph is not too hard. I did inline bytecode, it's even easier. I
Mm,
just bytecode parser, got a call, the inline heuristic said, do it. And I jumped and bytecode parsed over there. And so you got too much code thrown in that way and it blew up on you. And then the register allocator went crazy. C2s, the people ops were all pretty good with that. The loopy stuff was pretty good with that. Register allocator had a miserable time with that. That was what that was about with.
yeah,
And then when you actually ran it, you had iCache blowout. So
yeah, yeah.
that was not worth it. There are a lot of folks who said you compile everything, and no, fine. We had to try it. It was pretty clearly not going to work, but I had to produce numbers, so somebody got those numbers, and it sucked for obvious reasons. All right, what else? I'm going to call it early. Quality over quantity. Simon says rain stopped. Going home. Yes, I get it. Fortunately, we've had rain for days and months, really, and it's now not second day, not raining, and it's kind of nice out. I could go take a walk through the woods. Oh, that'd be nice. Call
I've
out
been
for
up
that.
for like way too many hours because I woke up yesterday at I think like 5 p.m., which is not good.
You woke up at 5 p.m.
I think so, yeah. I don't really remember because it's been too long. Yeah. I
No,
had some like I had some work piled up and I was like, oh, I'll finish it tonight, and I did. And so now I'm just up.
and now you're regretting finishing it.
Yeah. Well, yeah, now I'm not tired anymore, and that's the problem because it means I've like passed the like hoop
Yeah,
where now
yeah,
I'm just
yeah.
gonna stay
You
up.
keep going, you'll roll around, and eventually you'll be an early bird.
Exactly.
I have a funny story about staying. Like I used to do like Yasser and stay up all night, and now I just force myself to go to bed at like 2:30 in the morning or ish.
Yeah.
So,
All
but
right,
I
fine. I
keep
force
on
myself to go to
staying
bed
up.
at midnight. Fine,
Yeah,
yeah.
no, I mean, it depending on what else is going on in my life, I can set the time. But like what I like to stay up late, so I do. But when I was in my early 20s, I lived in this like kind of crappy third floor apartment. Um, but the landlord who lived just down the street had this daughter who was absolutely beautiful.
Oh, wait a
She was
second.
like the most like I had such a crush on her.
G rated.
Yeah, I just had like a total crush on her. And but she had a boyfriend. And anyway, I found out that she she broke up with him. Like he did something stupid and she dumped him. So I was like, oh, I got like, and she liked me a bit. So I was like, okay, I gotta like, except I was in this zone where I was going to bed at like 8 in the morning and like sleeping all day. And I could not like adjust myself to like be up at the right time to actually like go meet her. And so I completely missed out.
Wow, okay.
So
Yeah, I
yeah.
had a come to Jesus moment on my schedule when in college, and that was missing a test at noon because I slept through it. And that was like the one cheesy time I pulled one of these college stupid prank jokes out where I said the guy, I told the guy I had diarrhea and couldn't make it. And I got that from somebody else who missed tests all the time. Well, you have to have a ready excuse. Here's one. Just say you got diarrhea. Okay. Jeez, I felt so miserable for pulling that out. And I had to redo the test. And he made give me
Well,
the
of
harder
course you felt
version.
miserable. I mean, you were sitting on the toilet for how many hours?
Exactly. Exactly. I never let myself get that space again. That was bad.
So here's my funny story from today, which is which is funny because I've done this now 23 times and every time it's the same exact thing, but I just don't have enough cache memory. So it's like I flush the cache. So the next time I do it, I do the same steps, right? So it's like, okay, so installing a VM, right? So grab the ISO for Linux that you want to stick on there, right? And make sure you got a text mode one. You don't have a freaking GUI, right? Install the sucker with the minimum options. Go in, make sure the network's working, right? So how do you check? If config, right? And it's like, oh, I don't have if config. There's no such thing. So they're okay, right? I got to do a what is it? Sudo apt get, net install whatever the tools package for the network, right? It's like, don't have sudo. And at this point, like I go to the browser, I'm like, okay, I know I've searched this before 22 times. And sure enough, like I see the link kind of grayed out in my
Yes,
history
yes. You've
when
even
I'm
searched
looking
it in
for it.
recent
It's
memory.
it's like
Yes.
that's the one I want. Got to start putting Frankenstein together bit by bit.
Uh-huh. Experience is what you get when you don't get what you want. But you're supposed to hang on to the experience. All
It's
right.
like if you're traveling and everything goes perfectly, you have no stories. It's like how
Ah,
was your trip? Oh, great. Boring. You have to have some sort of disaster. That's why I never plan ahead. I just
great.
go, we just get in a plane and go and see what happens.
And see what happens. All right. Well, that was the skipping around the living room.
Yeah.
Yeah. We're gonna find out how she does this summer. We're gonna go to Europe again. Or she's gonna be walking every European step up and down and left and right, and
Fingers
maybe
crossed.
with or without crutches.
You
Jeez.
might not be doing the beach.
Might I be doing what?
The beach.
The beach should be good because
Well,
it takes.
I meant the the 4.5 mile hike down the.
Oh, that beach. Oh, Ballas. Yes, and the other beaches. We're talking Crete here. They had Crete has all the beaches that you see in all the travel brochures about the most beautiful beaches at Metro. They're all on Crete.
Hmm.
And this conference that we go to has one that's right up there as the most beautiful beach in the world, and the access to it is insanely bad and involves a significant hike along a very difficult trail.
And that's after you drive 73 miles on a 1 lane road with
Oh,
goats.
ridiculous. Yes. There are literally places where the road has, you're going through somebody's little village and the road, you could touch the walls on either side of the car as you're driving through.
Well, the wall on one side and the 500-foot drop
And then
off
there's
on
the
the
wall on
other.
one side and the 500-foot cliff drop on the other. Yeah. Yeah. And then the
And
goats will camp out in the middle of the road and block it. So you have to beat your way through the goats while not driving off the road. Yeah.
I did a long road trip in around the Peloponnese in Greece, and I found the Greek drivers to be terrifying because they come around these blind corners, but they pretend they're race car drivers and they cut the curve on the wrong side.
Yes.
And then when you show up, they go swerving and almost fly off the. There's like crosses everywhere on the side of the roads. There's like little shrines every few
Yeah.
hundred meters.
Yes. Yes. Somebody died here. I have driven many times on Crete. And I'm fairly aggressive in the U.S. And Crete's very mixed bag. There are a lot of folks who are just moseying along,
Yeah.
and then there are guys. They'll be in an Audi or Beamer, and they are just blasting by. And the bus drivers can be very aggressive as well.
Yeah.
Fine. All right, I need to go to the bathroom. And we had a slow, fun conversation, but it wasn't necessarily all about compilers, but it was kind of fun. There was a lot of fun stuff here.
We heard that.
Don't miss your exam.
Yes. Well, that's the toilet.
See.
All right. Bye.
Hi.
Till next week. Yeah.